Welcome to the Week 10 lecture for Microprocessors and Robotics. This week we've got another lab concept. We're going to be looking at arrays, how we program those, and we're going to look at using switch case in our labs. And then of course we'll have lab 8.0. And then we'll introduce a couple of other concepts this week. There will be no assignments on them, but we'll just go over the concepts. So those are going to be for inputs and outputs, the corresponding I/O interrupts, and some power management principles. The first thing that we're going to talk about this week are arrays. So an array is simply a collection of variables that are accessed with an index number. To shorten that, it's a collection of variables that we can quickly reference. So here we have how we would write it in C code. We see the type. So this would just be, for example, an integer. If you were using numbers, you would use char for character. If it was going to be a single character, you could do a string array. You're just declaring what type of variables your array is going to contain. That's all. Your array name is next, and that can be any label that you choose to give your array. Just like we've labeled other variables previously with whatever name you choose, you can label an array the same way, so just give it a name. And then in these brackets here, we specify the size of the array. So this is how many variables that the array is going to contain. And then after this, you have the option to either declare all of the variables in your array, or you can declare them later on in the program. You don't have to declare them. You don't have to declare your variables at the same time that you declare your array necessarily. So we can take a look and see how each of those options works. Here are a few different examples of how we can set up an array. So the first one, as I mentioned before, we are setting up without any variables. So to go over it, we're declaring this array to be a double type. We haven't really reviewed doubles, so think of this as like a character or an integer array. That would be fine. And then we're just calling this array balance. That's the name we're giving it. And in the brackets, again, we're putting the number of how many variables this array contains. So this balance array can contain 10 double numbers. The second example here, we are actually putting values into our array. So same thing, we're declaring what type of values, we're giving it a name, balance. We are only using 5 values in this array. And then if you want to declare your values right away, you would just put an equal sign and then use the curly braces. So one at the beginning, one at the end, and then you can plug in your variables and then you just separate them with a comma. So you can see our first variable is 1000.0, a comma, second variable is 2.0, comma, and so on and so on. So you can see each variable is separated by a comma. There are 5 variables all contained within those braces. It is important to remember that you can't have more variables within these braces than you initially declare at the beginning of your array. So we are saying we have 5 variables. We can't put more than that in these braces. We can put less if we want to leave some of those spaces open, but we can't exceed 5. Another way to do this to make sure that everything syncs up in your array, if you know you're not going to add anything else, you're just going to have the numbers that you start out with essentially, is we cannot put a number in here, or we don't have to put a number in here. So this only works if you are initially declaring your variables. You can't omit the number and omit the variables. You have to have at least one or the other, if not both. So here again, our array is called balance. We're not specifying how big it is, but we are plugging in all of our variables. So what this means is that the microcontroller is going to go through, it's going to recognize that there are 5 different variables in here, and it's going to recognize that the size of this array is 5. So the middle option is good, or the top option is good if you're going to be adding variables to your array later. The middle option is good if you want to add them all now, if you want to add some now, some later. And the bottom option is good to help everything sync up if you have all of your variables declared at the beginning. So we have a couple different options for declaring our arrays, but generally one of these is how you will set it up. So in our setup, we just looked at how to put numbers into an array, but we also need to look at recalling what spot those numbers are in. So if you declare your array, if the label we give it is called mark, the first element, the first number in your array is going to be referred to as mark and then 0 in brackets. So if I would put the number 7 here, when I called up mark 0 in my code, that would look to the first place in this array, and that would call up the number 7. And as you can see, this goes so on and so forth. We have mark 1, 2, 3, and 4. And so arrays always start with 0. They don't start with 1. They always start with 0. And if you need to find out the number of the last element in the array, then we just do the size of the array minus 1, of course. So this array, when it's declared initially, it might look something like this. We could call it an integer. And then we know that the label given to this array is mark. So we'll get that written out. And then this array contains 5 values. So we would put our 5 in our brackets. And then we could either stop here or we could put a curly brace and go on to put all of our variables in these curly braces separated by commas. And so we can see down here, this is essentially, I'll fill in the rest of these numbers, just some numbers in here. So if I wanted to call up the 5th value in the array, the number 8, I would have to reference mark 4. So that's the label of the array and essentially the element number. So I know my array holds 5. The last element is going to be labeled with a 4. If I want to call up the 3rd element, I'm going to use the label and a 2. So essentially whatever number element you need to recall, just subtract 1, and that's what number you'll need to put in the brackets. So now we'll look at a code where we can see how we are actually calling up numbers from arrays and how they can be useful. First, real quickly, this is essentially the same thing that we just looked at. It's got a couple different variables plugged in there, but this just shows what I just wrote out actually, that if we declare our array like we just did in the top with these initial variables, these labels up here, mark 0, 1, 2, 3, and 4, are how we would recall each value of the array. You can also use the different array numbers instead of recalling stored variables that you've already declared. You can also use the labels to put numbers or variables into those spots in the array later on. So I could deposit a value into the label test array 0 if I wanted to later on in the program. I could put the number 7 in here. Or I could put it in whatever spot I wanted, essentially within the array. So arrays are not used only to retrieve information, but you can also store information in your array later on in the program. Here's an example where we can use an array really practically to declare 6 different pins as outputs all at one time. So traditionally, if you have 6 different pins, you would have to give them all different variable names in your setup section. Then you would declare your variable names first, and then within your setup section, you would have to do this last line here, pin mode, right? And we would have to declare every single one as an output. That would be 6 different lines of code, but we can do this much faster with an array. So this first line up here is actually the start of our array. We're saying that everything in here is going to be an integer. And we're going to call our array LED pins. And you'll notice there's nothing in these brackets. We're not declaring the size of it. We're just going to plug in our variables and let it automatically calculate. So again, this is kind of the error-proof way if you're declaring everything in the beginning. That way you don't miscount. So we're going to be using LED pins 2, 7, 4, 6, 5, and 3. You'll notice they're not in that order, possibly for a reason. This might be the reason that we want to use these LED pins later on in the program, so they don't have to be in any specific order. All right, so we've declared our array. We finish with our last brace, and then as always a semicolon. And then we're going to just declare another variable. Pin count is going to be an integer and it's going to be equal to 6. So down in our setup, again, instead of 6 lines declaring the pin mode for each LED, we can do this in 2 lines with a for loop. And so this is another refresher of for loops. So we're saying for the integer, we're starting this pin. That's going to be our variable. So instead of using X or Y to keep it simple, like we've previously used, we're just going to be calling it this pin. It's going to start out being equal to 0, and then we're going to say, here's our condition. If that variable is less than the pin count, which remember is 6, then we increase we go through the code, right? We go through the loop, and afterwards we increase this pin by 1. And so our loop is just declaring the pin mode for LED pins, right? That's our array. And then it's going to declare, it's going to pull the value in the array to equal whatever this pin is. So stepping through that, that would look like, let me switch to a different number. So we would start at 0, right? So we would have 0 plugged in here. So what this would do is it would reference our array, and it would reference the 0 spot. So if we look up to our array, that's going to be the number 2. So then it's just going to declare pin number 2 to be an output. That's the pin mode, right? So then we're going to go through, check our condition. Is this pin less than the pin count? Yes. This pin variable of 0 is less than 6, so we're going to increase it by 1. So then it's going to be 1. Right? So then next this is going to go through the program and it's going to pull the 1 spot in the LED pins array. So then that's going to be the 7. So it's going to declare pin 7 as an output. And so this is going to continue. As this pin increases, it's increasing the spot here and it's just moving down the line in the array. So it's going to pull each spot one after another and declare all of those as outputs. So you can see how this could be more efficient. We're only using 2 lines of code down in our setup to declare all of these as outputs instead of a whole bunch of lines. Something else that we could do, if we'll use LEDs again just because it's a really simple example. If we had 6 LEDs connected, 1 LED connected to each of these pins, and we wanted to light these pins up in order, instead of having 6 different lines where we digital write the LED to be high, right? That's what we would use as a digital write command within our loop. We would have to say digital write, pin 2 to be high, digital write pin 7 to be high, digital write 4 high, and so on and so on. We can do that in a much shorter way. So we can essentially do that with another for loop. The only difference, or a couple differences, would be instead of pin mode, we would have our digital write command. I'm just going to put DW to abbreviate that, make it a little easier. And then instead of output, we would put high. And so this would be the exact same case. Of course, this would be in a void loop. And so what this would do, imagine if you had all of these LEDs in a row, is it would turn them on in order 2, 7, 4, 6, 5. I'm not sure why you would have them connected that way. Ideally, you would have your LEDs arranged on your board to kind of match up with your pin order. So it might look more like 2, 3, 4, 5, 6, 7. But if you don't, that might be why your numbers are in this order. And so that's really great. It's a great way for you to go through and turn all of those on. You could turn everything off just by using an array. And so you can see this is a much more compact way to do things. If you need to cycle through if you need to perform the same task, essentially, this is when you would use an array. If you need to perform the same task multiple times on different pin numbers, is a really good application. So anything that you want to plug in here, or if you need to perform the same thing on multiple variables of any types, right? We're not limited to pins up here. This could be word strings or inputs, outputs, essentially anything can go in an array, but if you're performing repeating tasks, that's when they're really good to use. Now that we've talked about arrays, we're going to move on to looking at the switch case statements and commands. So switch case allows for multiple choices within a section of code. So if you'll remember, if statements can allow for essentially two conditions, right? An if-else statement. If this is happening, then do this, or else do this, right? So that essentially gives two options depending on what's happening. We can give ourselves more options if we use switch statements. So they'll allow for several, essentially an unlimited number of specified conditions within your code. Now, you don't want to have 200 switch case statements essentially, but you can certainly use much more and you have much more freedom than you do with an if-else statement. So if you're looking for 3 or 4 different cases, a switch case is a really good way to establish that. So what a switch case does is it compares the value of some variable. You have some variable that you're looking at, and it compares the variable to a list. And it says, is it equal to the first case? Is it equal to the second case? Is this variable equal to the second case? And so on and so on. It runs through the program. When the case statement finds a value that the variable matches, so the case statement matches up with the variable, then it executes that loop. So you're essentially building in several mini loops into your program based on what the variable is. And then after every mini loop, you use a little break command, and that gets you out of the switch case statement, and you can execute the rest of your void loop. So the format for switch cases are actually really simple. The first thing you need to do is just the switch command. We just write switch, and then in parentheses you put your variable. So what variable are you looking at to see what you need to match up to? So this variable could be anything. It could be a word, it could be an integer, it could be a number, anything of that sort. So here, after we have our variable, right, we're looking at our variable, we are going to look at our different labels to see what it matches up to. And you'll notice each label has its own case. So this is our first case. We would put this label down here. If the variable matches the label, we'll execute anything in this mini loop, and at the end we'll break, and that will return us out of this loop to whatever is after the switch loop and into the rest of the program. And then here you'll see we have a second case that we could match with. Here's the label. So if our variable equals this label, then we'll perform this case. At the end, we'll break and exit the loop. And so as I mentioned, we can have a lot of different options with a switch case command. And because of that, how we add more options, here we only have two different cases, but so each option is called a case, and you can build several cases. It's just important to declare them with case, give them a label that you're looking for, a colon comes after that, and then whatever statements you want follow. And at the end of each case, this is very important, you need to include the break command. So this break command, again, just exits that mini loop so that you can go back to the rest of your program. So here's an example with slightly more detail. If we were looking for this variable to be equal to a number, if it was equal to the number 1, then we would perform the first case. And then you can see we would break out of that program into the main loop. If the variable was equal to 2, we would perform this second case. And then we have another option with our switches. So if the variable doesn't match any of our cases, it's some weird crazy variable, we can do a default case. And we don't write case in front, we just put it at the very end and we identify it as the default. So we're saying if the variable doesn't match up with anything, then just do this. So we can use that by declaring essentially a default at the very end of our program. So now we'll take a look at a more complete program using the switch case commands. Here's our program, and this is just off the Arduino tutorial site. but it's a really good example of how we can use switch case. So reading the beginning of this program, all the information is kind of contained in this code. I did copy it all over for your reference. But this code is essentially allowing you to choose from a set of variables, A, B, C, D, and E, to turn on different LED lights. So imagine, it even outlines it here, you have a circuit with 5 LEDs connected to your pins, 2 through 6. You have your LEDs connected and you want to turn them on by using different characters. So we can do this by using switch case. So of course we have our serial begin. We didn't declare these in before our setup, but we'll just imagine that they are declared. So in our serial begin, we're using that because we're going to be using our serial monitor to input the character value of the pin we want. We are using a for loop to declare all of our pins. So we saw in an earlier example, we used an array with a for loop to declare our pins all at once. Here we're just using a for loop. Why is that? Well, this time our pins are all in order. We're going 2, 3, 4, 5, and 6. And so we can just use a for loop and each time increment the number to declare that pin as an output. Where that array came into handy was that those pins were not all in order, so we couldn't just step up 2, 3, 4, 5, and so on. We had to jump back and forth between numbers. So just a note, that's why we used an array in one of the previous examples to declare all of our pins as outputs, and why we're not using it here, because the pins are in subsequent order this time. So we've declared all of our pins as outputs. Now we're going to go into our loop. And so we're going to prompt for an input with our line here. If serial available is greater than 0, right? So it's waiting for an input of some sort. And whatever is input is going to be an integer. We're going to call it in byte. And then we are going to read it in, right? So whatever comes in, we're just calling it in byte. That's our variable. So now we start with our switch. So we declare it with switch. We look at the in byte that was entered. And you can see we have several different cases here. So the first case is if the in byte was equal to A. So you will note numbers, we don't have to put in any quotation marks or anything. Like in the previous example, there were no quotations. If you're looking at different characters or different words or anything like that, then they need to go in single quotation marks. So you're not just looking for a number, you're looking at essentially a string, right? A character or a string needs to go in single parentheses. So this is looking to see if the variable entered was an A. If it is, then it's going to digital write to pin 2 and turn it on to high. So it's going to turn on the LED connected to pin 2, then it's going to break and go to the end of the program. And then if there's more program in this loop, it will go through it. If not, it will circle back to the top. So we have a couple of different other cases that we can look for, right? Because we have different input options. We have A, B, C, D, and E. And so for each of those, the switch is just looking through all of these cases to see where does the in byte match up with the proper case. And then once it finds that case, it will execute the little mini loop in the case. So for instance, if we entered C, it would execute this mini loop here, turning that LED on and then breaking out of the code. And then we also have a default. So if somebody enters an incorrect value or something that is not one of these letters, then it turns all the LEDs off. And you can see we're also doing this with another for loop. So instead of using 5 different lines to digital write all the pins to low, we can just create a loop, a little for loop, because they're all in order. And we can digital write the pins to low one by one very quickly. And so anything, again, that's not in expected input, that's not A, B, C, D, or E, then we're going to go down to the default case. and just execute whatever is within that loop. So this is how a switch case statement works. You don't have to have any specific number of cases. You can have essentially as many as you want. It's always a good idea to incorporate a default to account for those values. If you wanted to in your default, another option would be to do like a serial print, right? You could serial print the little message, try again. Your options are A, B, C, D, and E. You could do that to print out a message to the user to remind them to select a valid letter. You could give the user another option. You could do off. So if we declared in byte to be a string of words, then you would also be able to recognize off. So how we would do that. So within this case, instead of E within these quotations, we would just write the word off within those single quotations. And then we could write, essentially move this loop up here, and it would turn all the LEDs off if you typed in the word off. So switch case is really good, especially when you're expecting an input from the user, or if you're expecting an input somewhere else and you need something to depend on that. This gives you a way to declare a lot of different situations and create a lot of different mini loops and actions based on those situations. That brings us to your lab for this week. So the objective of your lab is going to be using those two main functions that we just talked about, using the array function and the switch case function. And again, the goal of these is more efficient programming, and the switch case function gives us more options when we're programming. So part one is focused on using an array. And you'll be connecting a series of 4 different colored LEDs to your board, and you will be ordering them not by pin order. So I note this in a couple different places. You'll be lighting them up not in their pin order. Here, mix up the order of connections. And so we'll just go through and I'll expound on what that means. So you want to connect your LEDs to different pins, right? So you have 4 different LEDs, connect them to 4 different pins. Do not connect the LEDs to the pins in the order that they're on the board. So don't connect your first LED to pin 2, the next LED to pin 3, and then 4 and 5. You need to mix up the order of those connections. And the reason for that is what I just talked about, right? So I want to make sure that we're fully grasping how an array is used. If we connected our LEDs all in order, we could use a for loop like we saw before to declare everything as an output in a row, to turn everything off all in a row. We can use for loops for that, which we will be using, but I also want to mix up the order to really emphasize how an array is useful. So if you have things that aren't connected in order, or variables that aren't in order, that's where an array is useful. So do that, mix up the numbers of your connections, and then we're going to use an array to blink these LEDs from the top of the board to the bottom, so from your first LED in order to the last, and then from the last one to the top one based on their physical location, not their pin number, but the physical location on the breadboard. So you want to have 4 LEDs all in a row, and then you're going to light them up going down, and then you're going to light them up going back up, essentially. So you'll just be making them blink, right? So you're going to blink the first one, blink the second one, blink the third, blink the fourth, and then you'll go back the other way, blink the fourth, blink the third, blink the second, blink the first. All right, so I gave you a hint here. You'll want to declare all your pins as outputs using that array, and then you can use this little for loop I've given you as kind of an example, or you can look back through the other slides in the lecture for an example on how to do that. This is just a hint. It's an easy way to declare everything as an output. A for loop is a good way to do that. And then you'll be using your array to blink your LEDs in the physical order that they're on your board. And then of course you'll just be copying your code here. And I don't have it noted on this little snippet of the assignment. I'll have to go back and add it. But you will need to take a little quick video of your LEDs lighting up in order. The second part of your lab, we're going to focus on using switch case. So for this part of the lab, to keep things simple, I do tell you to put your LEDs in order this time. So you just need to go ahead and switch which pins everything's connected to and put them in subsequent order. You could really use an array still if you feel like a challenge, but essentially it'll be much easier if you connect to them in order. So then we're going to use a character that coincides with the first letter of the color of your LED. So for this one, you'll need a couple different colors of LEDs. The first part doesn't matter. Part 1, you can use whatever colors you want. You can repeat colors. For part 2, you should ideally have different colors for these. So I think I am counting on you using 4 different colors. If that's not an option, you can reuse one, but try to use all different colors. And then just for an example, I remind you, if you enter a B, it should turn on the blue light. This is similar to the switch case example that we looked at before, where A, B, C, D, and E were turning on different LEDs. You're going to do something similar, but for this one, the letter should correspond to the name of the light. And then the default in your loop should turn all of your LEDs off. And then so here's a reminder just on how to start your loop and a couple things to double check if your serial monitor is not working properly. Now that we learned a couple additional C programming commands, we're going to move on to some other aspects of our microcontroller, such as our inputs and outputs and power management and things like that. So I've brought up this microcontroller architecture just to remind you of what it looks like. And so we've been using a lot of these components, right? But the one that we're going to focus on now is the input and output ports. So you've been using these, you may or may not have realized it, but we're going to cover these in a little bit more detail than what we have. We've just been using essentially LEDs, sometimes a push button for these input-output ports, but we'll cover what else these can do. So in short, the input-output ports of your microcontroller are responsible for connecting your little microcontroller board or the microcontroller in any format to an outside source. So they're the connections. The buses can help transfer data, but the input-output ports are where the connections happen. So a couple quick examples. A keyboard would be an input source, right, to a microcontroller. So think of the keyboard on your computer, that's providing an input. And in the same vein of your computer, the screen display would then be an output. So we have a lot of inputs and outputs that we can connect to microcontrollers to help us perform different tasks. So as I mentioned, you've seen a push button, or you've connected a push button to your board. That would be an input, right? That's looking for information. You might remember we actually declared that push button as an input pull-up. And then we've also connected LEDs, and we've declared those as outputs, right? So when we're declaring our pin modes, that's when we're telling our microcontroller that this pin is either an input or an output connected to something. When we're working with inputs and outputs, we essentially have to trick our microcontroller. Our microcontroller doesn't recognize that it has a push button or an LED connected to it and respond accordingly. That's not quite how it works. So the microcontroller just thinks it's reading or writing to some address. So for example, in our first couple labs, we saw we could read or write to registers, to memory locations. We can do the same with pin addresses, right? We use pin numbers as our addresses, and essentially the microcontroller thinks it's just reading from that address or memory location, or it's writing to that address or memory location. The microcontroller doesn't recognize that it is pulling in a signal from a push button or that it's sending out a signal to the LED. The way that we do that is the microcontroller board has been designed so that these signals can be translated into, or that the the information being input or output from addresses can then be translated into information to anything that's connected. So when we digital write an LED pin to be low, the hardware on our board, think of like the little resistors and other little components that you might see on there. That's what I'm talking about when I say hardware. So everything that's kind of built into your board helps translate those signals into things that our inputs and outputs can read. So when we say digital write high to turn a pin on, things happen in the hardware of our board to help turn that memory location, that address that it's depositing that information into an actual signal that then goes to our LED to turn it on. So we're essentially using the hardware of our board to trick our microcontrollers into inputting data when it reads a word at an address, or it outputs data when it writes a word at an address. So the microcontroller just thinks it's reading and writing words, but the hardware is helping us to communicate with any external connections. Now we're going to look at a few examples of inputs and outputs just to give you an idea of some possibilities here. So when we're talking about these, keep in mind that inputs and outputs can both be analog or they can be digital. So I've included the little wave snippet all the way on the right to remind you of the difference in these signals. So if you'll remember, analog signals, it's kind of hard to pinpoint an in-between value. We can kind of do that with an LED, right? You'll remember we use the fade amount value to set the value of our LED with an analog fade. Digital values are much more clear. Digital is essentially on or off. It is a value or it is not. There's no gray area. So that plays into our different kinds of inputs and outputs. Here are some digital inputs, and again, these are very, very clearly either on or off, or essentially inputting information, or they're not. So there is a push button, which we've used, right? It is on when we press it, off when it's not. There's an 8-button tactile board, so this is giving us multiple buttons that are all connected by a pin each. We have a photo transistor. It's detecting either there's light or there's not. There's no in between. There is a keypad where either you're pressing a button or you're not, right? So that's what makes all of these digital inputs. They're all used to provide information to our board. So our push button and our 8-button tactile boards are sending a signal if they're being pushed. The photo transistor is sending a signal if a light is on or off. And a keypad is, of course, sending a signal based on which key is being pressed. Some analog outputs that don't have an exact signal, or we can break it down into numbers to try to quantify the signal, right, like we do with our fading in LED, but they're usually between values, one point and another. There's some intermediate values there. So some of our analog inputs, the first one is a potentiometer. So this is a variable resistor, essentially. You can change the resistance. And what that can do is it can change like the brightness of an LED, for example. The more resistance you have, the dimmer it will be. And so this has intermediate values. It's not on or off. We have kind of in-between points. We can turn that little dial on top. We have a joystick that provides an analog input. So it's not necessarily one direction or another. We can move the joystick all around in different places, and that gives us kind of in-between like an in-between signal or an output. It's not necessarily clearly one value or another. So a joystick is an analog input. A piezo buzzer detects vibrations. So it doesn't detect is there a vibration or not. It can also detect things like the magnitude and stuff like that. So that's what makes a piezo buzzer an analog input. And here we have some digital outputs. So we have an LED. I don't think I have this on my next slide with the analog outputs, but an LED can essentially be both. It can be on or off, or we can set it to an intermediate value. So an LED is actually both a digital and an analog output. We have a 7-segment display, so this is an output that we can program to output some signal to the user. A DC motor is a digital output. We can turn the motor on and off using our microcontroller, and we can also program an LCD display using our microcontroller. So these digital outputs are all outputting information from our microcontroller. We also have a couple analog outputs here that are again outputting information from a microcontroller. So we have a piezo buzzer, not only detects vibration, but it can emit vibrations. And then we have an infrared range sensor, which can emit an infrared signal. So both of those are analog outputs. So when you're working with inputs and outputs in your codes and in your programs and in your projects, this isn't something that you'll have to typically worry about. They are at a simple enough level that they don't need interrupts, but more complex projects will require some input-output interrupts. So what does that mean? Well, our input-output devices are typically slower than a microprocessor to respond or to emit a signal, and so we need a way to sync those up, and so we can use an interrupt to do that. So a couple different ways. A device will indicate that it's ready for a command through the input and output port. So whatever you have connected is essentially ready. It's waiting to receive that command. And then the second step is that the processor issues a command to the device. So then the device indicates that it's busy, it's executing the command, and then once it's done, the input-output device finishes the task, and then it goes back to a ready condition. It's ready to receive the next signal from the processor. So all of this happens very quickly. That's why we don't really need to worry about it for simple projects, but for more complex things, sometimes we need to use interrupts as a way to sync things up so that, for example, our microcontroller isn't sending data faster than our output can receive it and respond. So think of like the LCD display is one of our digital outputs. If the microcontroller is outputting data, it's telling the display to display words faster than the display can respond, we're going to have an issue. So in that case, we might need an interrupt so that the display can let the microcontroller know it's ready. The microcontroller sends a message, hello world, that's displayed on the LCD, and then it can send a signal back to the microcontroller to say it's ready for the next display. So again, all of this happens very quickly, but sometimes it is needed to make sure that there's not essentially a data jam or that one component is processing faster than all of the others. So as I mentioned, there are two basic ways for our processor to use these interrupts to service the device. So the first one is polling, and this is processor initiated. So the connected device indicates it's ready, and a processor just periodically checks. So it's essentially like asking somebody, are you ready yet? Are you ready yet? Are you ready now? And so on and so on. So the processor is just checking the device constantly. If the device is ready, then the processor knows it can go ahead and execute whatever is next. So that's processor initiated. Interrupts are device initiated. So what happens is that instead of the device waiting for the processor to find out that it's ready, it essentially taps the processor on the shoulder and interrupts it and says, hey, I'm ready. Let's go to the next section, the next action, whatever we need to do next. So again, the first one's processor initiated. The device is waiting for the processor to notice that it's ready. And an interrupt, the second way, the device is actually interrupting the processor to say that it is ready. So there's two different ways that we can actually action these interrupts. Here's an example of an actual interrupt. We're calling it our interrupt service routine, or an ISR. This is pretty common here at the top. And so you'll notice this is before even the setup and before the loop. That's an interrupt needs to be before those things so it doesn't get caught in one of these loops after it. So this interrupt service routine is saying that, let me grab my highlighter. If we're digital reading the button, if it's equal to high, then digital write the LED to be high, or else the LED is low. So this example shows that even if the main loop is doing nothing, you can turn the LED on and off, or if the switch is pressed, that will also interrupt. And so the internal pull-up forces the pin to be high normally. When it's grounded, it becomes low. The change in the pin is just detected by a change interrupt. So what that means is that if we're in the middle of the loop, or if we're in the middle of the setup and the button is pushed, then it's going to go through the interrupt routine and turn on that light no matter what. So a good application of this might be an alarm, right? If you need an alarm to sound, think of like an e-stop if you're in manufacturing. No matter what's happening, no matter what's going on in the machine, you need that to immediately stop when you push that button. So an e-stop is the form of an interrupt, right? You wouldn't want to put your interrupt service routine into the void loop because then you would have to wait for your program to get there to detect if that button's being pushed or not. You wouldn't want to put it in the setup because then it would only look for it one time and never again. So by declaring this at the beginning of our code, that's essentially meaning we're constantly looking to see if that button's being pressed and to see if we need to execute based on that condition. So an e-stop is kind of an extreme case. But this is also useful for things like taking temperature readings. If you need to interrupt the reading, you could push a button and it automatically interrupts the code. If you have anything else where you need to detect something being pushed, or if you need to detect a certain condition happening, for example, if you detect a power overload, that might be where you would want to shut down a system. So you wouldn't want to wait if it took 5 minutes to get through the loop, you wouldn't want to wait 5 minutes to detect that overload. You would want to detect it immediately. So that's when you would put an interrupt at the beginning of your program to say, if this is happening, then we need to shut the program down, we need to shut the equipment down right away. And so these are just a couple ways that we can use interrupt service routines. This is a little bit different than what I just talked about. So we can use interrupts to sync up our devices, and we can also use them to quite literally interrupt a program. So there's a couple different meanings when we talk about I/O interrupts. The first is used to sync components, and then the next is to create quite a literal interrupt in our program for an extreme condition or something that we would want to suspend our program or execute some other portion very quickly because of the interrupt. Now we're on to our last topic of power management in regards to microcontrollers and in general. So the question you might be asking is, why do we need to worry about power management? Well, when you're working with microcontrollers and microprocessors, it's very important to be aware of this. One, because there are a lot of battery-powered applications. So from personal experience, I can speak to this right now. We're designing a new project or product at work. And the constant question everyone asking is, well, how are these changes going to affect the battery power? How is this function going to affect the battery power? Is using this light, having it on too long, is that going to affect the battery power? And so we're constantly looking at how things are going to affect the battery power, how we can maximize that. And so we're constantly doing power management. It's also important to note, if you're not very familiar with power management, differences of a few microamperes. So that's how we can measure power. So a very, very small amount of microampere can translate into months or years of additional operating life. So essentially every bit counts when you're working with power management. And the reason why we're so aware of this, why on my team we're constantly asking what the effect is going to be, is that it can make or break products in the marketplace. So if you think to a battery-powered product, it's really frustrating when those batteries die, right? For example, a lot of us have smartwatches, Fitbits, things like that, that we charge up. But then they run on that power, and it can be really frustrating if you are having to recharge that every day, every other day, as opposed to what we would expect to be like a week or 2 weeks. Same thing with phones, right? We see sometimes their phone life declines. It doesn't hold a charge as well. the battery is not doing so great. So that's not really an initial state, that's after a while, but as a consumer, we're always looking at the battery life of things. If you consider children's toys, you might want the battery to last for less time, right? Your child, of course, will appreciate a longer battery life. You might appreciate not having to replace the batteries as often. So people are always just thinking about products and how long they're going to last in the marketplace. And besides battery power, there's also it can be a marketing draw for other products, right? A lot of TVs now will say, they're low power, you can save this much every year by using this TV, or it only cost this much per year to power. Different appliances will say the same thing. It only cost, $12 a year to run a dishwasher, something like that. So the world is all about power management. Everyone's looking at how they can manage power, whether that's a battery powered application or another application directly plugged into a power source. So there's a couple main ways that we can manage our power. Two of the biggest things are the operating speed, or what we call the clock frequency. So if you're operating at a faster speed, of course that's going to draw more power. And something else that affects power is temperature. So at temperature extremes, you're consuming a lot more power. So for example, something that's battery powered in really high temperature conditions, that battery is going to have a much shorter life than at a room temperature condition. So clock frequency and temperature are two really big pieces that play into our power management. To try to make this a little bit more relevant to what we're doing, I brought in the specs of our MSP430 board to look at some of the power management pieces of that. So our board is 3.6 volts. It's designed specifically for low cost and low power consumption. It's a small board. It's not pulling a lot of power or using a lot of power. The idle mode current can be less than 1/1,000,000th of an ampere. So we talked about how important all of the amperes are, or how important amperes are, that even a small amount can affect your power management. So if you're not using your board, you're essentially in idle mode and it's not pulling very much power. It does have a top CPU speed of 25 megahertz, but we can dial this back if we really need to conserve power. The wake up times can be less than 1 microsecond. We can change those as well. So why this is relevant is if you were to use your microcontroller not connected to your computer, but if you were to connect it to a battery powered source, which you absolutely can do, you can connect it to a little battery pack quite easily, then you would really want to manage the power of your board. So the ones that we're using specifically are already designed for low power consumption, but if you had a different board, or if you were using some other microcontroller that you really needed to limit your power management on, you can look at some of these variables. So what is your CPU speed? What temperature are you using it at? What's your wake up time? So you can kind of adjust some of these features to find that balance between kind of optimum performance as far as execution goes, and balancing like a battery life or the power consumed. One of the ways that we can help reduce the power being used is by integrating some interrupts and a sleep mode. So we can essentially use a sleep mode in a microcontroller that is assisted by interrupts. So if you didn't have those interrupts and your microcontroller went into a sleep mode, the only way you could bring it out would be to reset the board. But by using interrupts, we can look for a certain input to bring that microcontroller out of sleep. So the most simple example would be a button press. So the board would be sleeping to conserve power, and a button press would bring it out of sleep mode. So that negates the need for a reset or anything like that. So an Arduino board, we're using a launch pad, but an Arduino is really similar. It has two interrupt ports, digital pin 2 and 3, that can be used as sensor pins to wake up and restart the code where it left off. So a reset starts over from the beginning. If we do a sleep with an interrupt, it will just pick up back where it left off. So for example, this Arduino board that's really comparable has two dedicated pins or not dedicated, but one of their functions is used, can be used for an interrupt port. We can even integrate special code depending on which pin triggered the wake up. So if it is pin 2, one thing could happen. If it's pin 3, something else could happen when you trigger the wake up. So we have a couple different options. We won't really be integrating these options into anything that we're doing in this class. That gets a little bit more complex. But it's good as something to be aware of, and potentially as you go out into the field and you're looking at power management and what you can do to conserve power, it's good to be aware of some of the basic tactics and how the different pieces of a microcontroller can work together to work on power management. Here's a few examples of some power saving commands. So I'm not going to go into a lot of detail on these because we won't be using them, but again, just to bring some awareness that this is a thing to be aware of. The first one is power mode. We can kind of declare what sort of power mode that our microcontroller is in. The second one is sleep mode idle. So that's one of our sleep mode options where the board just kind of idles in a lower power state. We can power down in a sleep mode. There's sleep mode power save, where you might be on reduced power, performing fewer functions. Sleep mode standby, the board might be waiting for something else to happen. So these are all similar in a way, but you can see we have a variety of different things that we can do with our microcontroller.